Hello everybody. In this video we're going to discuss one more detail about the losses in internal flows. And this is one detail that we didn't discuss before, and it's kind of different from what we were doing regarding the losses, the friction factor, and these things. But it's very related because it's also one type of viscous losses. And again, yeah, just to remind ourselves that this is where we are right now. We are still discussing the losses. The point here is that the losses are categorized into more than one category. There are two types of losses. What we have been discussing since the beginning of this chapter is what we call the major losses. These are due to the friction with the pipe walls, and it's calculated from Darcy equation as we showed before. There is another source of losses that is different from the what we call the major losses. The other type is the minor losses, and these minor losses are losses due to other sources, not just the friction between the fluid and the walls of the pipe. It has to do with the the uh, the shape of the pipe. It's not the shape, the pipe itself, whether there are any connections like valves, like expansions and contractions. So these are like sources that has nothing to do with the flow in the regular pipe. It's something that's added to the pipe that leads to more losses than the regular losses that happen due to the regular friction. We're going to discuss the sources of minor losses in details later, but this is just important to understand. So these are extra irreversible losses due to whether the change in the flow direction, change in the cross-sectional area, presence of valves or fittings. So these losses are called minor losses because in long pipelines their values are usually much smaller than the major losses, which is the losses we discussed before. That's why we call it minor losses. However, if we have shorter pipes, the minor losses might be more significant than the major losses. So it's not necessarily minor losses are smaller in value, but they are usually smaller in value. For all minor losses, and this is good news here, that the minor losses equation is very simple. It is calculated as follows. It's the KL multiplied by U square over 2G. So U square over 2G is the same as U square over 2G that we used in Darcy's equation. The KL is called loss coefficient, so it's a characteristic parameter for each source of minor losses. We said it can be due to the change in the flow direction, the change in the cross-section area, whatever the reason. For each one of the causes of the minor losses, it has its value of KL, which is the loss coefficient. And if we have more than one source of minor losses, let's say we have one change in direction, one change in the cross-section area, a valve, then we will add all of them. So it's going to be the summation of K times U square over 2G. And so the total losses that we have would be the sum of the major losses and the minor losses. The major losses are what we calculate from Darcy equation. The minor losses are what we calculate from this minor losses equation. So this is simply what we do. We just add one more term to the losses equation. It just depends on KL. And by the way, this KL, this loss coefficient, is available in tables. So it's not like the friction factor, like you are going to calculate it and do some iterations. It's much more simpler. You just look for the proper table and pick the number from the table and plug it in the equation. So it's much simpler than the major losses. So this is simply what we have. Sometimes we go through what we call or express the minor losses in terms of what we call equivalent length, and the equivalent length is simply that we say, for instance, the valve led to losses of, let's say, 1 over 4 of atmosphere. Okay, let's say 1000 pascals. Let's say 1000 pascals. So the equivalent length is the length of the pipe that will lead to 1000 pascals. So it's just to express this in terms of the Darcy equation. So the losses that happen in the valve, for instance, is equal to the losses that happen when we have a length that is equivalent, what we call an equivalent length. Okay, so this is the length of the pipe that will lead to the same losses as the losses we get from the valve or whatever. So if you equate two equations, u square over 2g will cancel out, and then we will have L equivalent equals KL d over F. So if we have a pipe that has length L with a valve, then it will have the same losses as the pipe that has length L plus L equivalent. So this is equivalent to this. So it's kind of something that we sometimes use this to make it only one equation for the losses, for major and minor losses. So we have just L instead of KL times u square over 2g plus Darcy equation. So this is simply what we mean by minor losses, and these are the causes of minor losses in detail. So we have 4 categories. We have the pipe inlets and exits. This is when flow is going in the pipe and coming out of the pipe, and we already discussed this in the beginning of this chapter when we were discussing the entrance effect and the entrance length. So this is what happens here, that for the fluid as it entering the pipe, there are more losses than usual, and similarly as it leaves the pipe. There is what's called expansion and contraction, whether it's sudden or gradual. So the expansion is the flow is going in a pipe with a diameter, and it goes to larger diameter. So it's called expansion. And contraction is the opposite, from larger diameter to smaller diameter. There are valves, which are devices that turn on and off the flow or control the flow. It's like the tap that we use to open and to open and close the flow of water. So these are called valves, and there are fittings, and fittings are connections that we use to connect pipes, to split the flow, to change the flow direction, to whatever the reason that we use these fittings for. These are also source of minor losses. So these are the 4 types of losses. Inshallah, in the next video we're going to go through each one of them in details and see how we can find the loss coefficient for each one of them. So I'll see you then, inshallah. Goodbye.